Okay, so let's go again and move on to this next section, which is discussion of sort of what the general linear model is, what we mean when we say general linear model, and sort of keep building our concepts. We'll start again with a tiny little bit of revision from yesterday, and that is this concept of a model. So we'll start here from this, basically revising what we mean when we say model. So a model we saw yesterday is a description of a phenomenon in terms of its most relevant parameters, the parameters that we're interested in. We're trying to get a simplified version of the world that doesn't have all the contents that the world's got. That model in our context is going to be linear. What does linear mean? Well, it's going to mean that the parameters that we're talking about, the parameters that we're using, are describing a straight line. So that's where the linear comes in. And what do we mean when we say general? We mean three things in this case. We mean that we can look at more than two variables, like we've been looking at, and look at multiple regression. Look at 3, 4, 5, 6, 7, 8 variables. That it's very basic to many different forms of statistics, parametric statistics. And then sort of close off by doubling back to where we started in the beginning, talking about all of this doing science and the scientistic type model. So that's where we'll go for the last part of the lecture. So when we're talking about a model, what do we mean? Well, we said yesterday that models can be physical. When we're building a model, a very sort of explicit physical model that everybody can relate to is this idea that Andy Field brought up, which was a model of a bridge, which makes explicit that what we want to do is we want to build a downscaled, downsized, or stripped back version of the world that's only got the features that we need for the physical task, if we're constructing a physical model, of the things that we're interested in. So if we need to build a bridge, we want to construct a physical model for testing, and we want it to have the right properties, and those properties is the shape of the bridge and not its colour. In statistics, what we're doing is not having an engineering task, we're not trying to build anything, we're trying to explain instead. So rather than constructing a physical model for testing, we construct a statistical model, and our requirement here isn't that we have the right physical properties, it's that we've got good parameters, estimates, and that we've got the right kind of parameters in our study, that we've chosen the right things to measure or manipulate, as the case may be. So that's model. And we talked about that yesterday. And we talked about the normal distribution as a statistical model with statistical parameters. And now we're not going to talk about distributions, we're going to talk about straight lines instead. So linear model, what do we mean when we say linear model? Well, we've already talked a little bit about this with figures like this one, where we have, say, two variables that we're relating to one another. Before we were relating fertility and life expectancy, we could be any two variables that we're measuring. Here, let's talk about how many years you spend in university, and this is always fun to talk about in humanities contexts, and starting income. So the convention here is that if you've got an experiment, what you do is you plot your independent variable on the x-axis and your dependent variable on the y-axis. So you can think of your input here and your output here. So the thing that you've manipulated down here and the thing that you're measuring on here. And we've been calling this independent and dependent variables. That comes within the experimental framework. We still think of similar sorts of roles for these variables, even when we're not running experiments. So we sort of need new terminology. So rather than saying independent variable, which implies manipulation, when in correlation studies and observational studies we don't have that manipulation there, let's call it predictor. So that's what we want to make our predictions on the base of. That's what we want to use to make inferences about another variable out in the world, or something else that we're going to measure. And rather than talking about dependent variables, which also implies manipulation, let's talk about outcomes. So now, instead of having independent and dependent variables, what we're going to have is a predictor and an outcome. And the outcome's on the y-axis. So if you think back to your tilde notation, which we're going to talk about at length, when we use this language of as a function of. So yesterday we talked about city fuel efficiency as a function of number of cylinders. Conventionally, you'd plot your cylinders on the x-axis and your fuel efficiency on the y-axis. And you'd call your cylinders your predictor, because you want to predict the fuel efficiency of a given car, given the cylinders that it's got. If you're buying a car, you want to know how many cylinders it's got first. You don't choose your car on the basis of its fuel efficiency in order to make an inference about how many cylinders it's going to have. That's not what you care about. So even though it's correlational, you still have epistemological interest in the way your variables are represented, in the way your model's set up, and in the kind of language you use. So let's take our linear model, and let's take a measurement. And let's take another measurement, and say that this is two people that we've measured, and one has been in university for 3 years, so they've finished their bachelor and they've gone out and gotten a job and their starting income was this. And another has done their master's or candidate and their starting income's this. So let's assume that these are the two measures. And we're going to model this relationship between these two variables in this sort of way. So we've got these 2 data points. Let's just start with a very simple 2 data point model. It's not enough data, but it's useful. The first thing we can do is extrapolate. So if we wanted to know what our assuming a linear relationship in education, let's just assume that education follows a linear pattern. If we want to know how much, let's say if we want to have an estimate, all else being equals, of how much our students will make after they finish one of these new 1-year masters programs that the government would like us to start running, what we can do is we can draw a line. And that'll tell us, give us a way of predicting very roughly what we should expect the starting income of any given student to be after they've finished the 1-year masters, or what we should expect their starting income to be after they've finished their PhD. So we can extrapolate. And so there's 2 things we need to know about here in order to make our prediction, now that we've got a straight line. There's 2 things that we're interested in. One is what happens when the predictor's not there. So what happens if you don't go to university? What's the baseline for any of this? And the other thing that we're also interested in this case most interested in, is how does change in one variable, or change in the number of years you spend at university, how is that related to change in the outcome that we're interested in, which is starting income? So they're the 2 facts that we want to know. And we can't do that with the tools that we've got so far. Because remember, all of the correlation coefficient stuff that we were talking about, what that tells us is the direction of the effect, whether it's up or down, and how cloudy the data are. So this is positive, so we can say that there's a positive association, so that being in university for longer is not going to mean that you're going to come out with a lower starting income based on this extensive study. But we can't say specifically what the effect of each year at university is going to be. How much increasing time at university is going to be associated with increasing starting income. We can describe this though, and we describe this using 2 things, 2 properties of this graph, and they're just properties of the graph. One we call the y-intercept, which is intuitive, and all we mean here is where does this line intersect with, or cross, or intercept the y-axis. That's the y-intercept, and the other is the slope. So that's the angle of this line. So how does this work? I have a very simplified example of this that I developed when I was mentoring PhD students, because people that don't remember their high school sort of linear algebra stuff can find it difficult to get back in touch with it. So I have an example that I like to run through, and I'll run through this with you now. So imagine that you've got a car. Some people find this useful, some people think I'm just saying the same thing over again, but it can be helpful to run through, to really consolidate this concept of what the slope means, what we mean when we're talking about an effect. Imagine you've got a car in space, driving as the crow flies. And let's say we're in Paris, and they're driving on a straight road. And they're 2 kilometres north of Paris. And the car drives northeast. The car's movement has both a northward component and an eastward component. The y-intercept is where the car starts, and the slope tells us that for every 3 kilometres east the car moves, it moves 3 kilometres north. So what it tells us is the change in y has an effect of the change in x. And how do we calculate that? We just divide the change in y by the change in x, and that'll give us this one. So this has moved, and this is wrong, I know. No, this is right. This has moved 3 kilometres north and 3 kilometres east, so the slope of this line is 1. And that formula always works. Why does that work? Because a slope of 1 tells you that there's a direct one-to-one equivalence in the motion of this car. So if the slope's 1, you know that for every 1 kilometre east you go 1 kilometre north. And for every 1 kilometre north you go 1 kilometre east. And all we're doing when we're doing linear modelling is just doing the same sort of thing. So let's calculate another slope. Car starts again 2 kilometres north. Now we can see that for every 2 kilometres east the car goes, it goes 4 kilometres north. Our slope is now 2. Why is that? Because for every 1 kilometre east the car goes 2 kilometres north. So the y-intercept tells us where the car started. The slope tells us how much distance is covered in the northward component for every unit covered in the eastward component. Is that okay? Okay, so imagine that we've got the car driving in years after university space and monthly income space. And it's just the same thing. So if we had a figure that we drew this line on, take the car away, put our data points back in, what this will tell us is that for every 1 year after university, this slope of 0.5, you'll get a change of 500,000 krone. Sorry, 5,000 krone. Wouldn't it be nice if you got 500,000 krone? So the y-intercept tells us that income when years after uni is 0. So the y-intercept tells you what you're going to make if you get a job straight out of gymnasium, or predicts that. And the slope tells us how much your income's going to increase for every year you're at university, assuming that there's a linear relationship. Okay? Or more generally, the y-intercept tells us the baseline of the outcome without putting the predictor in, and the slope tells us how much the outcome changes for each unit change in the predictor as an effect of the predictor. Okay, so let's look at some different slopes with different y-intercepts. So imagine you've got this situation: income and happiness, people working in business or in research. So let's say you've got some people who go out and get jobs in the industry, some graduates, and we want to look at whether or not staying at university to study more makes people, or whether or not people, so imagine, right, I'll get the example right. I'm getting a bit tired after 2 days. Imagine you've got a situation where candidate graduates go out and get jobs in industry versus they go back and do their PhDs. They become researchers. And as their income increases, both get happier. But the business people start off happier. So maybe there's sort of morose types stay in university. Then you'll have the same slope for the two, but a different y-intercept. So a different baseline. So what this would tell you if you found this out was that people who go into business are just happier before we even look at how much income they get. So they're happier people. Being in research makes you miserable. More miserable generally, and making more money is not going to change that, rather than going into industry. So this is the same, this is different baselines. So this is different things happening when there's no predictor variable. What does this mean? Oh, it means that there's the same effect of income on both groups. So that increasing researchers' income makes them just as much more happier as increasing people in industry's income. So that income's not interpreted differently in terms of the happiness that it causes. You might run the same study and find the same baseline but different slopes. So that if two people, if you discount for their income, nobody gets zero income, but imagine we've got data points and we can draw the line so that we get down to zero income. We might find out that if we extrapolated from our data from both groups, imagine there's lots of data points here, lots of data points here, that both groups are equally happy when we don't take into account the effect of income. But as income increases, then people in industry get happier, but people in research get more miserable. They could be doing administrative work. So I can imagine that this is the sort of slope that you could perhaps see. So the same thing happens here when there's no predictor variable, but there's different effects. So that giving people more money in one case makes them happier but makes them sadder in the other case. But here we might have an intervening variable, which is administrative load. Yeah?
Could you explain why there is no predictor variable? The predictor variable was on the x-axis, right?
Yeah.
So that's income.
That's income here. It's not years after university here. That's income.
Yeah. So I don't get the point about there's no predictor variable. What
did I say that? Oh, when the predictor is zero.
Ah, okay.
That's all I meant. Sorry.
All right.
Yeah, now I know when I said it.
Yeah.
Yeah. So when we set the predictor at zero.
Okay. Yes.
And so we have to do this hypothetically because nobody lives off no income.
Yeah.
So we have to extrapolate our line down to where the effect would be zero.
Okay. Yes.
And then we'll say these two groups have got hypothetically have got the same baseline.
Yeah. All right.
They'll be equally miserable. But thank you for that clarification. So here we have a negative effect for research and a negative effect for positive, a negative slope for research, which would mean a negative effect. So that as the income goes up, happiness goes down. Okay, so you've got these concepts, you've got these ideas under your skin. How do we model this? We model this using the linear equation from algebra. So we model this just using this functional form that you're used to, which is the equation for a straight line. So all we're doing is we're drawing a straight line through our data clouds, where the y is the y value, the m or the a for the Danes in the room. I don't think I've ever found another country that uses a, is the slope, the x is the x value, and the b is the intercept.
How do you know whether it's legitimate to draw a straight line? How much on the line do your data points need to
We'll
be?
do that in the very last exercise where we look at nonlinear effects. But until then, we'll assume that the lines are always straight.
Then couldn't the R help us?
The R could help us to tell about how cloudy the data is.
Yeah.
So Leah's question could be, how do you even know that there's a straight line
Yeah.
that you could draw? And we'll talk a little bit about that as well. But another question is, how do you know it's a straight line and not a curve? Because remember, if you put a square on this x, you get a parabola. So how do you know it's not a parabola? And both questions are important and we'll address them both. Okay? So y-intercept is your baseline and your slope's your effect. So if y equals mx plus b, you can think of that as being outcome equals slope for a value of your predictor. So a value of your outcome is equal to the slope times a value of your predictor plus the y-intercept. And we write it like this. We don't use the ax plus b notation. We write it like this instead. But it means the same thing. So what this means is, you can think of this as effect. Okay, so B means effect. So a score, remember I means score. So a score y on the y-axis should be equal to the effect of 0, the effect null. Right, so that's your A, and we don't times that by x because we have the B here, it's the same one here, plus the effect of 1, so the slope of the line, times the score on the x-axis, plus this error term for score 1. And this is where we're going to start to address Leah's question. Another way of thinking of it is score on your independent variable, if you're comfortable with that language, or score on your outcome, your y-intercept or your baseline, your effect of your regression coefficient or your slope, score on your dependent variable, and your model error. And this is the new part now, so how do we deal with this? What is model error? Okay, so let's go back to our example from the beginning, where we have population and life expectancy. Yep?
Sorry, can we go back to the last slide?
Yep.
Yeah, I don't understand the y and x here. Isn't the y depending on x? When you change x, the y changes depending on that?
Yep, it does. Y changes depending on x as a function of the slope. So y, your y value that you get, is your x value times the slope of the line.
Yeah, I get that, but
Yeah.
isn't x the one you manipulate?
Yes.
So that's the independent one.
Thank you. That's an error.
Oh.
Yeah, no, you're right. Thank you very much. You spotted an error in my slides.
Sorry.
Yeah, no, it's good. I will fix that now. I've been using this slide for many years and glossed over that. I'm sure that somebody's told me that before and I forget to fix it. Yep, no, that's an error. Thank you for that.
Okay.
Yep, so that's a mistake. Okay, so let's go to an example again, where we have population on the x-axis and life expectancy on the y-axis. And let's start this time with our model of some linear relationship. So let's say we have a model of a linear relationship between these two variables. And that specific relationship is that y is equal to 1x plus 1. So y is equal to a slope of y, any y value that we pick, that we want to find, we can predict by knowing an x value. So we just choose a point here. Let's choose, I don't know, let's choose 4. Go up to the line that we've drawn, which we know has a slope of 1, which allows us to go over to the corresponding y value, and we know to put this line here because it's got a slope of 1 and it's got a y-intercept of 1. So let's start with a linear model. In reality, we start with the data, and the problem is that real data don't follow the exact straight line that we've got here. So how do you know where to put the line? This is where you use this error term. So what's this error term? What the error term does, and this should be something that you're sort of familiar with when we were talking about standard deviation, when I showed you those plots for standard deviation, when I showed you the plots that we used to build up the concept of R. So again, we're developing new concepts here, but we're developing them in such a way that we're using the old concepts again. So instead of standard deviation, which tells you the average distance from each data point to the mean, now we want to know the average distance of each data point to our line, which is our theory, which is our model. So what E tells us, or E of 1, so E for score number 1, this epsilon, to be more accurate, this error term, what that tells you is the difference between your linear model and your real data. It also tells you how well your model explains your data. So if everything goes according to your theory, then all of the dots will line up perfectly on the line, and your theory will be 100% accurate. You'll have a perfect explanation. If a cloud starts to form, your explanation gets worse. As the cloud gets bigger, the explanation gets worse and worse and worse and worse and worse. You can also say it tells you how well your model fits the data. So a perfect fit would be when all of the dots fit the line. perfectly. They follow the line perfectly. As the cloud gets bigger, it fits worse and worse. Also call this the error term. Again, this is in the statistical sense of error. This is the world being erroneous relative to my beliefs. It's not error as in I made a mistake measuring things. It's also called the residual. It's an important term, which just means the stuff that's left over after the model. So it's the residue. So if you ever hear people talking about residuals, this is what they mean. Just this epsilon term. Okay? So how do we calculate that? We follow the same procedure that we followed until now to find these distances between data points and values, or data points and lines. So let's take one of the data points, where I is 3. So that's this one, y3. We know what BO is, B0. We know what B1 is, that's the slope of the line. We know what x3 is. That's just the data value, the value for the data point. What's epsilon 3 in this situation? It's just here. The distance from our dot to our line. This is our model error, our residual. Is that okay? It's very important. It tells us about how good our fit is, it tells us about how good our model is, and it essentially answers Leah's question. How do you know whether or not your line's any good? It tells you how well any given data point I follows the model. So if you want to know for all of the data points, then what you do is you calculate this error term for each of the data points and add them up. If you add them all up, that'll tell you how well the data as a cloud follows the model. We've got a very familiar problem by now, which is that you can't just add these things up, because you'll end up with the signs cancelling one another again. So if you take the data point minus the model, this would be positive, this would be negative, 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 positive. We want a positive number always. So we end up with the same problem. So we can't just add because the signs will cancel. So what do? We do the same as we did for standard deviation. And we called that the sum of squared residuals. Why is it the sum? Because we're adding them all up. Why is it squared? Because we square them to get rid of the sign. So the distance between the line and the data point squared, then add all of those distances up. That gives us the sum of squared residuals. Okay? Or the sums of squares. But it's exactly the same concept as standard deviation. Really, it's standard deviation for models, not for means. Is that okay? Okay, so more specifically, it's called the model sums of squares. So this is the distance of all of the data points from the line. This is a measure of how good the model is. But we need some sort of reference point, right? So it's a measure of how good the model is, but what does the model mean? It needs to be relative to something. What does goodness mean in this context? What is our goodness relative to? So we could have drawn any line, right? We put the line here, but we could have put it here, or here, or here, or here. Why put that one? Why put the one that we did? It's kind of another way of interpreting the question from before. Well, linear models can be better or worse. All of these lines are going to have different residual sums of squares. They're going to have different added up error terms. So if I draw a line that perfectly fits all of these, then this one's going to be way off. And the amount that this one is off will mean that we lose all of the value that we gained by moving the line over here. So the model will become worse if we had a line that went through this one. So we need something that goes through the data so that it minimises overall the residual sums of squares. So when we're talking about the best model, what we mean is the one with the lowest residual sums of squares of all the possible models that we could have put on there. And that's what your stats package does for you when it gets a linear model, is it finds that best one. And so we call this line then the line of best fit, which is intuitive. We call it also the regression line, or the line of least squares, which all means the same thing. But what it means is that the line through this cloud of data that's simultaneous, that gives you the minimum for the sums of squares for all of the data points combined together. And we want to be able to quantify this fit. We want to be able to quantify how well our model fits our data. That's one of the things that we're going to be very interested in. So how do we do that? Well, we start to go back to a concept that we started the day with. We go back to variance. We go back to variability. How much of the variance, or how much of the variability, how much of the data cloud can be explained by the model? What does the model add to the data cloud that the average couldn't do on its own? So essentially what we're doing here is we are increasing from some baseline by adding this best fitting line. And what we're increasing from is just the average of all the data points. So yesterday we were talking about averages. Now we're trying to do a little bit better and fit a line that is best for both variables at once. So average here just means total variability, total variance, so the variability of outcomes around their own means. We do that by taking the sums of squared of the model, which is the distance of each data point from the model, and divide it by the sums of squared, which we call the total sums of squares, which is just the error in the data without the model added. So this is the distance to the averages, like what we did this morning. So this is, if we consider the model with the influence of the predictor, and this is without the straight line that we've added through the data cloud without the influence of the predictor. And if we divide that by this, it gives us this standardized number that tells us how good our model is, which is constrained by two things. How noisy are our data generally? So if we've got a really, really cloudy data, it's going to be hard to find a really good model. But if we can find a line that fits reasonably well, we'll get a pretty good score. And that is called the R-squared value. So this is this combined minimizing error term function, this straight line through the data cloud, divided by how noisy is the data, how cloudy is the data generally. And so then, what we say is the line of least fit, or this regression line, this trend line that we've put in, the one that we end up picking is the one that has the lowest R-squared. The highest possible R-squared. And we're seeing R-squared here. We've seen R before. Does this have any relationship with R that we were talking about before? It does. It's just the R that we calculated before, but squared. That turns out. Okay? So really what we've been doing for the last part of the lecture, last 30 minutes or so, is taking the linear equation from high school algebra and adding the stuff that we did on correlation in the beginning, putting them together and squishing them together. And that gives us this framework for making inferences using a statistical model. Okay? So before we move on to talk about what we mean by general, we encounter this problem of scales again. And here, this problem can be more or less serious, depending on what your explanatory goals are. So if I want to talk about things like fertility and life expectancy, I'm actually interested in talking about the world in terms of those scales. It makes sense for me to make predictions that are in those terms of those scales. It makes sense for me to say increasing fertility, for every one extra child you have, your life expectancy will decrease by 5 years. and it clouds the issue to convert that to standard deviations. But there might be some cases where it's actually useful to standardize and convert to standard deviations. So sometimes we might need a standardized scale. So sometimes we might standardize and sometimes we might not. R gives you unstandardized regression coefficients or unstandardized B values, B1 values. Is that correct, Adela? It's unstandardized, right? I think no, I think it's unstandardized. Okay, so how do we do that? Well, we just calculate a z-score again, but I won't go over that again. And so when people report the small b, generally, what they're meaning is an unstandardized model, and when they report betas, they mean a standardized model. However, this terminology is creeped back over here for some people, so sometimes you'll see people talking about their betas in an unstandardized model. Sorry. How do we interpret this? Well, this b value, well, as we've seen, it's a slope, or the slope of our predictor, and we can think of this as an effect. Just like we talked about the effect yesterday of the difference between two means. And just like two means can look different due to chance without actually being different, this slope can look different to zero even though it's not. So again, because we're in the null hypothesis significance testing framework, we have to worry about this kind of error of finding something that's not actually there. So that means that we might be interested again in significance, the significance of our slope. So our null hypothesis then is that the slope's 0. And our alternative hypothesis is that the slope is not 0. And how do we find out what's going on here? How do we find out whether or not a slope that's not 0 in our results is due to chance or not due to chance? We do a t-test and we get a p-value. Okay? Should we have another break or go on? Break. You're going very fast today. Either everyone's so exhausted that nothing's going in, or but we're moving very quickly. I'm worrying. Is everything okay?
You are moving. I find you moving fast today.
Okay. I haven't got a couple of the people who were slowing me down yesterday aren't slowing me down, so someone needs to take the slow me down function.